Alright, so there's two major rules that we have to use with capacitor simplification. It has to do with when we have capacitors in parallel, and then when we have them in series. There's different mathematics for each. So by parallel, I mean if we have a battery, and that battery is hooked up to a plate of a capacitor, and then the other side of the capacitor is hooked up to the negative terminal. We could call this capacitor C1, and then if we have another one hooked up like this, that's going to be C2. And this is two capacitors which are wired in parallel. Now we got a voltage of the battery, let's say it's a 10 volt battery, and we want to try and simplify this circuit so that we can analyze how much charge is on each capacitor. So let's give the capacitors some numbers, like 1 farad and 2 farads. Now, there's a few facts about circuits that we got to remember from what we studied before, like when we did the lab recently, and that is that in any one loop around a circuit, you have to lose as much potential as you gain. It's a conservation of energy idea. So, in going through this first loop here, we would gain 10 volts of potential when we go through the battery. And you don't lose hardly any in the wires, especially if there's little to no current. And you gotta lose that 10 volts somewhere. And so the only place to lose it here, for the most part, is the capacitor. Alright, so there's going to be a 10 volt potential difference across that capacitor, which means the left plate is going to be at 10 volts, and the right plate will be at a potential of 0 volts. Now, that is called, in circuits, Kirkhoff's loop rule or loop law, which says that the sum of any potential differences in a complete loop has to equal 0. So if you gain 10 going to the left through the battery, you got to lose 10 going through the capacitor. Now we can write that mathematically. Say the delta V of the battery plus the delta V of the capacitor has to equal 0. Therefore, since we gain 10 volts in the battery, we can solve for the delta V of the capacitor, and that reveals that the delta V of the capacitor must be negative 10 volts. Alright, so it's good to think about the potential changes as you move around a circuit loop. Now, if we analyze the other loop, that would be going from the battery around this path. Call that loop 2, or this is loop 1. Same thing has to apply. You got to lose 10 volts in loop 2. So we're going to have our positive plate here at 10 volts, and then our negative plate, 0 volts. It's a general rule of thumb that when points of a wire are in contact with each other, like this, all these points are going to be at the same potential, roughly. Unless there's a high current flowing, you shouldn't really lose a lot of potential in the wire itself. So these points are in contact over here, so they're all at 10 volts. That's the idea. Okay, so now that we've labeled the potentials, we want to simplify the circuit to figure out how much charge exactly goes on each capacitor. So the way we simplify it is to create a new circuit diagram based on the old one, where we replace the 2 capacitors with just one. It's called CEQ, which is an equivalent capacitor. And it's supposed to behave exactly like the other 2 would have. So it's supposed to take on just as much charge as they would have. But there's a rule for finding the capacitance of CEQ, and that's this rule. CEQ for parallel circuits is going to be C1 plus C2. You add their capacitances. And so our CEQ then is going to be 3 farads. That would be the sum of those 2. Let's now try to figure out, in the imaginary situation, how much charge would go on the imaginary capacitor. So for that, we just use the rule C equals Q over delta V. So we're going to have 3 farads equals Q over 10 volts. Therefore, our charge is going to be 30 coulombs. And that's helpful, but it is important to note that that's not a real capacitor. There's no one capacitor that 30 coulombs is on. It's on a combination of these capacitors above. So we have to use our reasoning about how coulombs work, like what exactly charges are, to figure out where these charges go. So it can't be that both of the capacitors have 30 coulombs on them, because coulombs can't be created or destroyed. If you got 30, they have to be spread out among these capacitors. But it's going to be 30 total, though. Okay. So what can we do next? We can use the rule on just one of the capacitors. Instead of focusing on the equivalent capacitor, we could just focus on one individually. We could do that one or this one. Alright, so if we apply the C equals Q over delta V rule to just this capacitor, what would that look like? Well, we would have C1 equals Q1 over delta V1. So you apply it just to that system. It's a lot like Newton's second law, how you can apply it to a system of your choice. That's what you want to do here. Let's plug in the capacitance. That one's 1 farad. We're going to have Q over 10 volts because that's the drop in potential across that capacitor. So your Q is going to be 10 coulombs for capacitor 1. Then you want to apply C equals Q over delta V to the other capacitor. So for that, we'll use C2 equals Q2 over delta V2. This is a 2 farad capacitor, so it's going to be capable of holding twice as much charge. They have the same potential difference, but we find that Q2 is going to be 20 coulombs now. So the puzzle here is complete. The first capacitor holds 10 coulombs. The upper second capacitor holds 20 coulombs. Together they hold 30 coulombs. And so that's why the CEQ equivalent capacitor has some relevance to the situation, because it shows that, yeah, together, combined, they do hold 30 coulombs. But you have to analyze them individually to see what portion of those coulombs go to which capacitor. Alright, so now let's try a capacitor in series problem. If they're in series, they're wired in a loop, so that they are both part of a single loop now. Let's let C1 be 1 farad and C2 can be 2 farads. Got a 10-volt battery. According to Kirchhoff's loop law, if we go through an entire loop, we have to lose as much potential as we gain. So let's create an equivalent circuit. The equivalent circuit has just one capacitor, which is a theoretical combination of the two original capacitors. It's called CEQ again. Now it has a different formula for series. The formula is CEQ for series will be 1 over C1 plus 1 over C2. It's a little bit more complicated math. So let's find our CEQ for this situation. It's going to be 1 over 1 plus 1 over 2. And then when you enter that into calculator, you can do this. I get 2/3. Two-thirds of a farad. So the capacitance of the equivalent capacitor is always less than the two original ones if we're talking about series. And that's because of the gap, you know. If you put the two gaps together, it's twice as much of a gap, you know. Okay, so now that we know that, we can now figure out how much theoretical charge this equivalent capacitor would attract. So you want to do CEQ equals Q over delta V. Now in the theoretical simplification of the circuit, we see that there's only one capacitor in the path there, which means that theoretically that capacitor, the imaginary capacitor, would drop 10 volts because the battery has 10 volts. So that's what we would use for delta V, but we got to use 2/3 farad as our capacitance of the equivalent capacitor. So our Q is then going to be 20 over 3. Yeah, it's going to be 20 over 3 coulombs, which is approximately 6.67 coulombs. When we're in series, though, what should happen is we should push 6.67 coulombs of positive charge onto this plate, and we'll push negative 6.67 coulombs onto that plate. And what happens with the metal in the middle is it just polarizes. Negatives are attracted here to the positive, and then positives are attracted to the negative there. So what happens is both capacitors end up sharing the same amount of charge. And so that's always going to be the case for capacitors in series. So C1 and C2 have the same Q as CEQ, but they have different voltages. Contrast that to the previous situation. We said in the previous situation they shared the same delta V. So C1 and C2 have the same delta V as CEQ. So that's just a little bit of the differences between capacitors in parallel versus series. Okay. Now we can analyze each of the capacitors individually to see what their potential drops really are now. All you do is you apply the C equals Q over delta V to each of them individually. So you got to use C1, Q1, and delta V1. Well, we know C1 is 1 farad. We know the charge is 6.67 coulombs. And then we can solve for delta V. Delta V is going to be that first capacitor drops 6.67 volts. Then you do C2 equals Q2 over delta V2. Plug in 2 farads, 6.67 coulombs. So delta V2 is going to be 3.33 volts. Alright, yeah, so delta V1 is 6.67 volts, delta V2 is 3.33 volts. So the capacitor that isn't as good here has to have the larger potential difference in order to attract the same amount of charge that the better capacitor can attract.